Thank you very much. It's been quite an exciting today. I'd like to say that today we now have got water back in our house. Great improvement since this morning. For now, I'd like to thank the organisers for inviting me to give this plenary talk. And in conjunction with myself and Professor Dowley at University College Dublin, we would like to share you some information about microwave generated steam decontamination of respirators and face masks. The work was conducted over the last 6 months, and we've all been in the pandemic. So the motivation is in 2 parts. In 1918, the influenza pandemic was caused by the H1N1 virus. In 2006, it was well published throughout the scientific community that there's going to be a lack of PEE in the United States strategic stockpile. In 2009, we had the H1N1 pandemic again, and it affected younger people rather than old people because the older generation had some resilience from the 1918 pandemic. In England, there's quite a famous 57-page and heavily redacted accessible version of the 2016 UK exercise called Cygnus, which reports about the use of PEE in pandemics, and it was heavily criticised because it only mentions PEE 5 times and slightly discussed distribution stockpile PEE. In 2019, the SARS-CoV-2 erupted and is ongoing. Today, we are participating in a virtual conference due to SARS-CoV-2, and there's still a lack of PEE around the world. Second motivation, this work. In the late 1990s, you could get microwave steam sterilization of infant food equipment through shops. So we know that microwave steam sterilization works for killing bacteria. MGS, which is microwave generated steam contamination of respirators, started to appear in scientific publications in 2010, just after the second pandemic. Used single-use PE has been destroyed all over the world. It's not been recycled, it's just been destroyed. There's an urgent need for reuse. That is 3 times of N95 respirators. I'll discuss what N95 means in the next couple of slides. If we engineer the published work of MGS decontamination of respirators, this has a great green chemistry potential. And that's what we need if we want to get out of the pandemic in an orderly way. Everyone's looking at how to reorganize industries using green chemistry and so on. So, the outline of our talk. I will present a slide on microwave oven and cavity magnetron background research done in England and in Ireland. I will discuss the N95 respirators and SN95 surgical respirators. I will then go on to discuss green chemistry and microwave generated steam contamination of respirators, looking at chemical engineering, scale out and process intensification. Then I should go on to microwave oven hazards. If we're going to use microwave generated steam, we must understand the hazards. And from that, I will go on to the thermodynamics of microwave generated steam. Then I shall give you sort of a layman's way of understanding microwave oven technology and MGS technology. Then I shall go into the 6 published papers on this subject, 4 of them from the 2009 pandemic and 2 from the 2019 COVID-19 pandemic. Then I shall give you some do's and don'ts. Then we should go on to recommendations. Current recommendations, what you can do today, and what we can do in the future. Looking at green chemistry, scale out, processing, specification. So this is a heavy slide. Don't be afraid of it. All it is 9 papers, starting from 1998, where just after leaving the Cavendish laboratory, I was designing, building, and selling into the semiconductor industry microwave oven plasma reactors for decontamination of iron in plant ceramic insulators up in Scotland. And we looked at different ways of controlling the microwave arcs, plasmas, and discharges. 20 years later, while I was at University College Dublin, I repraised all of this and published 4 papers on conversion of microwave ovens into plasma reactors, compared microwave oven reactors to single mode reactors, looked at how microwave ovens could be used as a rapid processing tool. Then I went into more esoteric magnetron modes and the chimera state in chaos theory. In the last year and a half, we published on microwave oven plasma reactor moding and its detection. Again, the chimera state and its instabilities. And last year, we published on application microwave oven plasma reactors for the formation of carbon-based nanomaterials. This paper is actually coming out at the end of this month in spring, proceedings of complexity. Okay, we've all gone through the pandemic. We all have type 1 respirators, face masks close by. And in the surgical teams, we have N95 particle respirators. And the S means surgical respirators. What they mean is that they filter 95% of 0.3 micron airborne particles, typically the size of a SARS virus, hence the name 95 in America. I've shown you 3 types of respirator, all 3M. They are the 8210 N95 particle respirator. Notice it has a metal nose clip, and look at the length of the nose clip. It's typically 11 to 12 centimeters. This is the free wavelength of microwave radiation in your microwave oven. So those metal nose clips resonate at the frequency of the dry frequency of a magnetron. I show you another. Next one is a 180-1860 surgical respirator. This has not only a front filter, but it has foam to absorb moisture, liquids. And another one below, the 3M 1870 surgical respirator. Again, it has foam. This one doesn't have a nose clip. So we have problems. So what I'm saying is we have problems with resin metals, wavelength of the same dimensions of the microwaves, and we have foam which collects water. Today we're all talking about green chemistry, principles, how to get out of the recovering from the pandemic. How are we going to use it? All industries are going to re-gear to green chemistry. If government's going to put money in, they're going to put it into the green chemistry. And I outlined the first 12 basic principles of green chemistry. I won't go through them all, but they start from prevention of waste to building inherently benign chemistry for accident prevention. We can scale up, or we can use green chemistry for the microwave generated steam. And if we use green chemistry, we must go into process intensification. That's to look at each individual step of the process and integrate each step prior and post step to get maximum efficiency. Okay, I'm now going to start to talk about microwave hazards, and the first thing we need to understand about microwaves is they're different from thermal heating. If we heat a pan of water, it comes from the outside in, and it heats up the molecules slowly from the outside to in. Microwave processing means that the radiation passes through the liquid and absorbed by the molecules themselves. So, and it heats from the inside out. And the molecules vibrate and heating by friction. Under specific conditions, if we put a pan of water into a microwave oven, leave it absolutely dead still in a vessel which has got no cracks, it's got very clean surfaces, it's very difficult for bubbles to be generated. And what you can get in this situation is superheating above 199.9 degrees. Typically, it will heat up to 105 degrees before any evaporation starts. So what happens is that, I will show you in the next couple of slides, when you take out a superheated liquid vessel out of the microwave oven, the jarring upsets the water, and what happens is you get an explosion of steam, the equivalent of the drop of 5 degrees. And that, in the next couple of slides, this is what happens. If you take out a superheated liquid out of the microwave oven, it explodes and all over your face. And this is a classic example of what happens when things go wrong in a microwave oven. The next two slides are two studies, one from the United States and one from the UK. In this study in 2013, I give you just one slide, and it shows the difference between adults and people under the age of 18. I like to show you where the maximum number of areas of burns. For adults, was the hands and fingers. For people under 18, it's the head and neck. That's to say, younger people who are smaller height get it right in the face. People of taller stature, typically adults, get it on the hands and fingers. And for medical advice, since 2010, they've been screaming, put child-proof locks on your microwave oven if you have a family. In the UK, we've got another paper in 2016. The subjects are the ages range from 26 up to 50, female and male. And a surprising thing here, in 2016, the source of the accident was from unpierced tins, canned potatoes in this case, boiled eggs, poached eggs. So what it's saying is that if you put a sealed vessel inside a microwave, you're going to get a face full of heated liquid, either from your can of potatoes or a poached egg. And notice that it's all in the forehead, eyes, the eyelids, and these the outcome of the treatment can last up to 16 months. Okay, I've shown you some gory stuff, but now I want to go back into a bit more into science, a bit more, in actual fact, into school level science. When we went to school, we all did the colorimetric calculations of heating of water. The first equation is the power is equal to the mass times the specific heat capacity of water times the change in temperature divided by T. And so we can heat up some volume of water in the microwave, and we can calculate the energy in the water. If we times equation 1 by seconds on either side, we get the quantity of specific heat required to raise the water up by a given temperature. This is all classic school level stuff, and we're going to use this to understand what's going on in microwave generated steam decontamination. So what I've done here, do a worked example of 100 grams of liquid phase water, heating from 22 degrees up to 99.9 in 1 minute. We do the standard equation, it gives you 154 watts. Okay, now let's assume that we have superheating, which is another 5 degrees. And what we get is from 105 degrees down, we get an addition of 35 watts. If we take this 100 grams out of the microwave oven, that 35 watts will be convert water into steam. If we look at the latent heat evaporation of water, we know it's 2.26 kilojoules per gram, and we know that 1 gram of water yields 1.67 litres of steam. From this, we can calculate 35 watts converts 0.015 grams of water into 0.009 litres of steam. Of course, the primary aim of microwave generated steam decontamination is to kill all the bugs on the respirator, and we can use the respirator again. So we've heated it up to 199.9 degrees. And what we want to do is carry on the process for another 120 seconds or thereabouts. This would yield 65.28 kilojoules, which will convert 29.6 grams of liquid water into 49.5 litres of steam. So what I'm saying here is that we can calculate the rate at which we reach boiling point, and after that we can calculate the amount of steam being generated. And in all accounts, it's the steam that's killing the viruses. The next slide, I've taken a very simple type 1 mask, medical mask. We've all used them. And I've shown it in figure A. Figure B is the actual metal nose clip, which is covered with PEP or PVC. And you can see I haven't got a scale on it, but it's typically 11 to 12 centimeters. Now I've put 2 of these used nose clips. The mask be used for hours, and what happens is they burn from the ends because of the radiation of 12.2 centimeters. But if you get a kinked piece of metal, then it will start to burn at the point of the kink. Notice in the D, it's burnt from the either end. So that was a nice straight piece of metal put into a microwave oven. So, okay, do your microwave in your kitchen. The microwave oven is rated at the back of the oven. It gives you 110 or 100 or 240 volts, and it gives you the amount of energy in power, so many watts. This, in some papers, people will quote this value, believe it or not, but that's the value of the total power going into the microwave oven. We don't want that. What we have is a microwave magnetron, what's called a packaged magnetron. Yeah, it's packaged cavity magnetron. Of course, all the magnets, they're all built in there, and they cost about a couple of dollars. Again, we do not want the rated cavity magnetron power. That is the power coming out of the magnetron into the waveguide, not into the cavity of the microwave oven. What we need to measure is the available cavity magnetron power. This is the microwave radiation within the oven's cavity, and it's based on the open water bath calorimetry measurement, which I've discussed earlier, and how to calculate it. Next thing we have to understand is in the papers, some use industrial type microwave ovens, where they put the sample in the oven and it's a magnetron at the bottom and the top, and it radiates from the top and the bottom. To scatter the microwave radiation, they use paddles in the waveguides. In domestic microwave ovens, we put the water bath on the carousel and put the respirator on top and let the carousel move. And you see side illumination, so you get more even illumination of the load. In this case, I'm using the term very precisely, the complex impedance load, because we have water and a mask, which have different microwave properties at different temperatures. So we're going to call it a complex load. A little bit of science, unfortunately. Cavity magnetrons were developed in the start of the Second World War. Classically, 8 resonators coupled in a ring. Each second cavity is coupled, and the one next door to it is 180 degrees out of phase. This is what we call the pi mode of operation. To the right, we see that the magnetron is placed in a fixed position on a fixed piece of waveguide from the cavity. The complex load rotates, and what happens is some of the power gets reflected back, not as coherent, but as incoherent waves, and it upsets the wave pattern within the waveguide, and that upsets the magnetron and moves the frequency. As long as the complex load doesn't move the running frequency of 2.45 by plus or minus 100 megs, the magnetron will always work. It's automatically matching. So you put your item into the magnetron, into the microwave, and it works, as long as the magnetron operates plus or minus 100 megahertz. In microwaves, put metal into a microwave, you get an arc, plasmoid electrical discharge. And this has been well known, and we developed an Airfield Probe back in 1998 for the semiconductor industry to identify this arc. And all what it is a piece of wire connected to a neon, which you might find in an electrical plug. So the arc strikes, electrical discharge excites the neon. You put a photodiode next to the neon, you see the light going on and off, on and off. And you can turn this on and off position to the external circuit of the microwave system to turn it off. So you do get an arc, which generates into a fire. The neon will light up, photodiode will detect it, and you turn your microwave off straight away. Technology's been there since 1988. Some other things you must be aware of. I am going into the nano field now of making nanomaterials in microwave ovens. Again, this is deliberate to make bubbles. We use a piece of metal, which is a quarter wavelength bent, so it will generate high stress fields at the ends. And that's where the water will break down into the gas molecule, into gas bubbles. And that's where we can start to build nanomaterials in the vapor phase of the bubble. Some people use quarter wavelengths on copper plates. Again, the length of the wire LM is proportional to C over operational frequency over the dielectric constant. Below, we have to go back 100 years or a little bit more than that to Pick's empirical formula. I have discussed this many times in my other line of work in chaos. And this VG is the voltage gradient where the visual corona of an arc will be first be turned on at the point of the tip, what we call the corona inception voltage. So this equation tells us that if we have a disruptive electrical gradient on a wire, which has a surface roughness from 1 to 0, a relative air density from 1 to 0, and a tip radius measured in centimeters, we can calculate the electrical stress on the tip of the electrode. So if we want to get the minimum voltage gradient, we make the tip very small, we make the surface of the electrode very rough, and we try to get to a lower air density. So that's the microwave stuff out of the way with. How do we compare one paper with another? Typically, we use the power density. This is a value of watts per litre. So we know the amount of power going into the chamber, we know the volume size. We can look at all the papers and get a rough idea of how much power per centimetre or per litre there is. The other piece of information we need to know is the process energy budget. That's the time, total time, how much converting power into joules, and for the time of the process, we can calculate the total energy budget of the process. There are two ways of doing microwave generated steam: in the open water bath or in sterilizer. Mothers who have children will know the sterilizers very well, because that's what all the papers have been using. Go to a shop and buy a microwave sterilizer and put your respirator inside it. Okay, heavy slide. I understand this, and you look at this in shock, but there are 4 main papers for the pandemic 2009, and there are 2 main papers for 2019. There are other papers which look at different aspects, but these are the 6 papers. So the work has been going on been started for the first pandemic in 2009 and the second pandemic 2019. And we will look at their data now. Okay, this table shows you the first 4 papers. We have the microwave ovens. We have the power, watts per feet or liters per litre. We have the amount of water. We have the way it's been heated. We can calculate the radiation time, and we can calculate the process energy budget. A lot of this data has been taken from supportive material. In our full paper, these are the references below. And for the SARS-CoV-2 pandemic, we have the microwave oven. The first one by Pascal, and Zulef doesn't actually tell us what microwave oven he uses, so we don't know the volume, but it gives us the rated power for the 2 ovens. We can calculate the radiation time, and we can calculate the budget, the rated budget. But we have started to see some discrepancies in the data. We're having holes. And this is, shows you power density. First 4, we're at about 28 to 30 watts per litre. Pascal is the industrial regular microwave oven to Magnetrons, so it's way up at 100 watts per litre. And so if we can only do a guess from looking at the pictures and understanding the type of microwave oven he has. So I'm going to redo this now and look at the input and output calculations of the water bath decontamination process. We have the power process budget, the water, temperature range, the heat, to raise it up to 99.9. We have the remaining energy budget, which convert water into steam. And here is the liquid being turned into steam. Now, liquid we can turn into liquid, so typically 25 to 41. The grey area of this slide is the known measured available power. All the other people are presenting rated powers. Notice that there are twice the amount of power in the rated systems, not the measured ones. So we have a discrepancy in the power measurement. We know that. It's always the case. People take their magnetron, look at the rated power and assume that that's it, not the available power. Again, we've done it for the sterilizations. We've got the true available power for Fisher, and we get the process budget. Pascal, it's really high, but we know it's rated power and it's for 2 magnetrons, so we know there's a problem there. We can look at the energy to raise up the water, and then we can also look at how much energy is available to convert to steam. Again, look at the last column, 20.3 compared to 40, and we can convert 34 rather than 70 litres of steam. This is one of the main problems of the papers so far. Okay, this slide is looking at all the masks reported in these papers. First, also in America, we get 3M, and we have 3 outcomes. We have the BEF, the arc adhesion, and the Waugh test. Okay, the BER is bacterial efficiency filtration. That's to say, if the system mustn't degrade after the decontamination process, must still have the efficiency of the filtration. And you notice that microwave generated steam for 1 pass, they all pass that test. They don't arc in these particular papers, but they do fail in the adhesion. That is and this happens in the surgical masks. What happens is the foam inside the mask separates from the body of the mask. The Waugh test is a test which came later after 2015. This is the water absorption retention test. If you're decontaminating a mask using microwave generated steam, you inevitably get water in the mask. And it's a well-known fact that medical doctors do not want to put on a damp mask. They typically do not want to put a wet mask on. So this is a very important test. People, Fisher particularly, have used this test to measure the amount of water in the mask after decontamination. Generally, you have 9, 8, 9, 11 grams after 1 hour. The process is useless. The medical person will not put that mask on. What it tends to be is the surgical masks that tend to fail. But also, we're nice to see that the type 2, which is what we commonly wear as a person in the street, fails completely. The BEF completely goes. You can't put a type 1 or type 2 mask in. It just fails completely. Adhesion, again, fails on a number of occasions, but they tend to be surgical masks. And we had this one occasion that we have an arc. Again, what happens is that the arc burns a hole in the filtration body of the mask. So it's, again, totally useless. So what I'm going to show you is some do's and don'ts from the papers. It's been found that if you use a cup of water to put your mask on and put it in a microwave oven, it only partially decontaminates the mask. What you need is a very large volume, typically 2 to 3 times the surface area to put the mask on top of the water bath. That is now you can start to decontaminate the mask. If you bottom left, I've shown you a Ziploc bag with a mask inside. This happens to be a type 2. Okay, what happens is that it gets soaked, first of all, but also the bag itself bursts upon radiation. So you can't use a Ziploc bag. Again, this is anecdotal in the papers. What seems to be the best way of doing it is to put your mask in a sterilizer, which is used for decontaminate baby bottle cleaner, and you have a problem of getting this inside the microwave oven. So the size of the cavity is an issue, and that's going to be something you have to look out for. Okay, and come with some recommendations now. You at home, if you have a microwave oven in your home, use it as a decontamination system. Make sure that any grill is removed. Check for signs of cavity, surface, or joint corrosion. Again, if you're using a lot of water, you're going to get corrosion in the cavity, and that's going to change the voltage on the surface of the cavity. So, and then we are heating water, so we're generating steam. A lot of microwave ovens have vents at the front of the door. You want them at the back. So if you have a lot of water coming out the front, you're going to have scalding. So you can't use that type of microwave oven. And the number 4th on this list is perform a calorimetric test of the oven. So work out how much power you actually generated in the microwave oven using open water bath test. If you're going to go off and buy a microwave oven, you have 5 points you need to realize. You want a minimum cavity magnetron of 1,000 watts to allow the available power to be 750 watts. You want a minimum of 70 litres, free working space. That is to say, nothing's obstructing the 20 litres. So you get your sterilizers in now. I've not stressed this point much, but you need CW mode cavity magnetron. Normally in domestic microwave ovens, that's the last possible dial turn. Pulse mode, like you use for defrosting, is no good. It has to be CW. If you're going to do this at home, then you need a childproof operation if possible. So look out for that. Again, if you can, inside the store before you buy, do a calorimetric test to measure the available power in the oven's cavity before purchase. Okay, what do we do in the future? We're coming out of the pandemic. Everyone says we have to change our way of manufacturing. So we have to not scale up, but we must scale out using process intensification, using green chemical engineering. We have 3 objects. We have the respirators, the sterilizers, and the microwave oven. They all have to be integrated for the microwave system to work. So for N95 and S95 respirators, we must replace the metal nose clip with a polymer or composite which is stable between 80 and 110 degrees. We have to find new ways of bonding or embedding and securing the nose clip into the respirator body, which also will survive 3 cycles of both steam and microwave radiation. Thirdly, we also have to lower the absorption and retention properties of the surgical masks. Again, if it's a load of water in the surgical mask, the practitioner will just throw it away. So what's the point? If we look at the sterilizers, we see that people are using sterilizers used for cleaning or decontaminating baby food products. It's not beyond the wit of designers selling these equipment. The redesigned equipment to hold more than one N95 respirator, multiple. Can we get 4 or 5 into the sterilization system? Secondly, if we incorporate an anti-superheating device, such as a quarter wavelength metal electrode, which will generate bubbles, it prevents superheating. Therefore, we have less risk of scalding or burns when you take the system out of the microwave oven. To the microwave oven itself, we need a minimum of 20 litres to get your sterilizer in and out safely. The manufacturers have to supply the oven's average available power, so we know how much power is going into the system. Steam vent extraction ports at the rear of the oven, again, take away the steam away from the door. And if you're in a doctor's surgery, you can plumb this out through the back window or something. Again, it reduces the hazards of steam. As in all the papers I've shown here, which are 2 on the medical side, they all implore that microwave oven designers incorporate a childproof lock system. Adults know what they're doing. Unfortunately, children have to learn. And the best way to do it is put a proof lock, childproof lock on the system, and the process can then be controlled by a responsible person. Next thing we have to do is go back to 1998 and incorporate an Airfield Probe to detect arcing with a circuit for automatic oven shutdown. Again, this will stop fires happening, and you go online, especially in the States, you read about all these fires in homes because people putting masks into a microwave oven without any water, and it bursts into flames. Lastly, I've not talked about is nickel electrolysis plating of the cavity. Don't use stainless steel; it's got a high resistivity. Use one which has got nickel plating. It reduces the loss of the cavity, and it keeps the oven cavity Q factor high. I've not gone into this, but we can direct you to some papers on that. That is the end of my talk. So I'll leave it to you to ask any questions.